Hi everyone, welcome to today's session. Today's session is going to be about DNS packet, DNS header, DNS message, and DNS flags. So, we are going to cover in detail things about the DNS, domain name system. So, let's start with seeing how we normally do the resolution for the DNS on our system. Let's check on the command prompt how the resolution part looks like. I'm going to do a resolution test for youtube.com. NSLOOKUP www.youtube.com. This is going to give me a result showing the IPv4 and IPv6 addresses. Here I have used the NSLOOKUP tool, which I have talked about earlier in my videos as well. So do check those. This is the address IPv6 DNS server, which have responded back to us with a non-authoritative answer, giving us some IPv4 and few of the IPv6 addresses. This is how a normal resolution happens. Once we have seen how the DNS is resolved using the lookup command, now we can see what's the purpose of DNS. DNS is normally used to resolve the domain to the IP address. And all the discussions which we are going to do in today's session are taken from the RFCs 1034 and 1035. So it's all documented how everyone used these DNS and how unanimously the DNS is defined. Starting with what is domain name system? Let's look at the definition. It's the easiest way to define DNS. DNS is a distributed protocol which works via delegation. In this, we are going to see distributed protocol, which means DNS is highly distributed, which can be understood by thinking how we earlier used to resolve the domain to IP thing. Earlier, there was etc host file being used in order to get the IP address information for a particular domain, and that was a static information where someone manually needs to define domain to IP mapping, and then only we can fetch. But in order to scale this approach, the domain name system was introduced, and this works via delegation. So delegation is a thing how we are delegating the domain from top to bottom approach in a hierarchical namespace. How the root is going to delegate things to the top level domain, and then top level domain is going to delegate the name server record information to the further levels. So in order to understand the delegation part, we will need to understand how the hierarchical structure looks like. So when we are accessing anything on the browser, for example, maps.google.com, so we normally go ahead and type maps.google.com. But how actually it is read in the domain name system language, it is going to be maps.google.com dot. Normally after com there is a dot, but we do not see that on the browser. In order to make things easier for us, it's not visible, but dot is always present there. So starting from the top, so that is how the parsing happen in the DNS system. It's from right to left, and we normally write from left to right, so it's the other way around. So root is the top level, then there is a root is above the top level domain, then the top level domain is these com and in domain, then there will be a second level domain which are the famous one, Amazon, Starbucks, Google. Then there will be a subdomain level which might or might not be present for some of the domains, like Google have maps.google.com, drive.google.com. So this is the hierarchical structure, and this is how we define the levels of domains. Now how the delegation works. In order to understand that, we will need to know that how levels are distributed into different zones and how that works. So in this example, there is a .com zone which is the top level domain. Then further there is a second level domain, which is Google, which creates its own zone, which is named as .google.com zone. Now here we have two different zones, .com zone and .google.com zone. .com zone is going to delegate things to the .google.com zone, and that is the beauty of the DNS system. Here we are delegating things. In the .com zone, we have primary name server. Primary name server is a name server records which provides us more info about the authoritative name server, where exactly we need to look further in order to get the domain IP mapping, or where is the actual record present. So name server provides us the authoritative name server record information. So in the primary name server, we have a zone file, which is a simply database to store information. So in primary name server, which is .com, we are going to look into a zone file. In primary name servers, the zone file which is present is editable, which comes up with a read and write access. So we can perform different operations on it as well. Operations like create, update, and maintaining. We can do all those changes. Now from that zone file, the .com zone is going to delegate things to the .google.com zone, which is the secondary name server, which is again going to copy the zone file from primary name server to itself. And that is simply a copy which do not come up with any operation access. So we cannot perform any kind of operation on it. And we also need to understand, in the zone, the top level is always known as apex. So from where the zone start, that is the name server record, and that consists of the zone file as well. Starting point is known as apex. So here we have two apex, there are two different zones, and in within a zone we can also have the terminals. So the endpoints are also known as terminals. Next, we are going to look into the DNS message. So DNS message is a combination of fields which we have in the DNS and how a packet is created. So in the DNS message, first of all, let's look into the DNS message, which says up to 512 bytes. So DNS message comprises of DNS header, question section, answer section, authority section, and additional section. And these are all very important sections we have in the DNS message. The DNS header is a fixed size of 12 bytes, which is never going to change. Further, we have a variable size which can be up to 500 bytes. Question, answer, authority, and additional. These all sections can be up to 500 bytes, which is a variable size. And this combinedly forms a DNS message which can be up to 512 bytes. Now further, we can also see the DNS normally uses UDP header. That is why we can see 8 bytes of UDP header. If the 512 bytes of DNS message is anytime exceeded, at that time there will be a switch of protocol from UDP to TCP, because TCP gives us more reliability while sharing a big chunk of data. So once our message size will exceed, the recommendation or the process how DNS works, it is going to switch from UDP to TCP. Further, we have the IPv4 header, which is of 20 bytes, and this all entirely makes up IPv4 datagram. Till UDP header, it forms UDP datagram. Further, we can move and see what are the fields DNS header have. So let's check those. DNS header is again of 12 bytes, and it comprises of different fields like identification, and there are 8 flags present in it, which comes with their own unique use cases. So we are going to cover those use cases next in the video. So keep watching. Next we have the question count, answer count. So basically DNS header is providing us the information like identification, which is important in order to make sure we are able to map the question, the query with the response of it. So whatever the DNS query, we need to map it back with the DNS response, and it can be late in the time as well. It is a possibility. So how we are going to identify? We are going to identify it with the identification ID, which is going to be of 16-bit, and that is going to be unique for each and every query we raise towards the DNS resolver. Further, we have flags with different use case, and then we have the count, which tells us how big the variable size of the DNS message is going to be. Questions, how many questions are being asked in this particular query, how many answers we are getting back in the answer response, then what are the authority records, what are the additional records. Additional records consist of a lot many things: opt records, glue records. So that's all the useful information, but this is how the DNS header looks like. Jump into the questions section specifically. So question section consists of three fields, which is also known as three tuple resource record information. The name, what is the domain for which we are going to fetch the DNS mapping. So it can be www.google.com. Further, we have the type. What is the type of this resource record? And then the class. So type can be like IPv4, IPv6, then class can be internet. We are searching this for this on internet. We have the answer section. Answer section gives us the 6 tuple resource record information, which is the name, type, class, time to live. So name, type, class are common from the question section. These are further very important fields like time to live. So time to live tells for how much time this information is not going to get stale. Once the TTL value gets expired, now this answer is not anymore reliable. We need to do the resolution part again. The TTL has expired, this will get vanished from all the caches, and we cannot rely on this answer. The response data length. The response data length tells what is the response data. First of all, it can be IPv4 or IPv6 address, how long that address is. That is the data length. Let's jump on to the DNS flags now. DNS flags, starting with the query type and opcode. So these flags are mostly 0 and 1 and depends how many bits are being used there. So query type is a single bit, which can be 0 when it's a request type of query, and it can be 1 when there is a response, when it's a response of that query. Opcode, it's a 2-bit of flag, which can be further used as a value as 0, standard query, value is 1, it is going to be inverse query. Inverse query is also known as the pointer query, and it is used to first provide the IP address and then request for what is the domain mapped with this IP address. So it's a reverse process. Standard query is normally when we are providing the domain and asking for its IP address. Then we have a value is 2, which is server status request. So whatever the DNS server is going to respond us, what is the status of that server, whether it's available or is it reserved. If value is set to 3, the server status is reserved. So these are the flags used mutually by the request side as well as by the server side. So these fields represent the client as well as server at different stages. Further, we will jump into the other two flags, which is authoritative answer and the truncation. So authoritative answer is again a 1-bit flag which comes up with either value 0 when it's a non-authoritative answer. If the value is set to 1, it is going to be a authoritative answer. Then we have the truncation. Truncation is again a 1-bit flag which can be either 0 or 1, but this is a very important flag. Truncation flag is going to decide which protocol DNS is going to be used. whether it is going to use UDP or it is going to use TCP. So if value is 0, no truncation is required, it is going to work with UDP. If value is 1, which means DNS message have exceeded the 512 bytes of DNS message optimal length, here either we need to perform truncation, either we break that DNS message into smaller parts, or we go with the TCP as a protocol in order to pass on the more reliable information. So there is a shift of UDP to TCP for reliability. Next we have recursion desired and recursion available flags. Now recursion desired is again a 1-bit flag which either says it's not desired or it says yes it is desired if set to 1. So if it is a recursion, it needs to move from one level to the other level in order to search for the answer. It's a recursion desired. If recursion available, so basically recursion available is set from the server side. If a value is set to 0, the server says recursion is not available. If it is set to 1, the server says yes, recursion is available. If you want, I can recheck from the main authoritative name server whether we need to update the answer here, or you can simply use the cache value. So that is how we are making sure no expired or stale entry is responded back to the DNS query. Then the last two flags which we have are 0 and R code. So 0 is again a simple flag which is a 3-bit reserved subfield normally set to 0, and this will come to use if we are going in the advanced settings of DNS in order to include the protection or security. So in those cases we are going to use or change anything in 0, otherwise it's set to 0 by default. It name also defines 0. So next is R code. R code is a 4-bit subfield, and this is again one of the most important flags after the truncation. So R code is a 4-bit subfield which is going to denote whether the query is answered successfully or not, and how that is we are going to achieve that by the value of it. And this, there are going to be a lot many values than I have shown here because it's a 4-bit subfield. So we can go 2 raised to power 4, which is 16. 16 errors can be identified by default, and we can even exceed the R code bits in the advanced settings. So simple values represents no error, problem with format, server failure, name error, request type not supported by server. So that was all for today's session. Thank you so much for being with us. Do subscribe our channel and keep following us, keep supporting us so that we can come up with more information. Thank you.